All right. I have remembered to set it to record. I have 11 o'clock, so we will go ahead and get started. Uh, some more, I'm sure, probably will join here in a few minutes, hopefully. But first thing, just quick reminder, review, recap what we were doing yesterday. What we were doing yesterday was in section 1.4 in your book. We were calculating normal stress that's due to an axial load. So we've got a member that's just being exposed to an axial load, no bending going on whatsoever, and our normal stress was P over A, where, well, focus. Again, the P here, that is the axial force that's normal, perpendicular to the cross-sectional area. And A is obviously the cross-sectional area. And so that's the formula we're using to calculate normal stress. We did an example yesterday. We had a bar with the different cross-sections, different axial loads applied. And that was where we got to yesterday. And I want to work one more example, calculating normal stress before we move on and start talking about shear stress. So again, I'll pause for a second. Anybody got any questions related to normal stress before we work another problem? No questions. Maybe I'll do what I've done the last couple of days. I want to hear from somebody, so now I'm looking at my list over here. Andy Lee, I haven't picked on you yet, so if you would, unmute and say hi, let me know that you're out there.
Hey, Mr. Walters, can you hear me?
I can hear you fine.
Wonderful.
Good morning. Thank you.
Good morning.
All right. I just like to hear somebody every once in a while. It gets kind of like I'm isolated in a cave up here. So, all right. Well, let's do another example. This one, again, is going to see how much you remember from statics because we're going to look at a truss. So this is an example we're going to work. We're going to try to find the normal stress. And each member of the truss. All right. So our truss is not a big truss. It looks like we got three members. And we've got a pin support here at joint C. This is joint B. And here at A, we've just got a roller. And we've got one external force apply here of 500 pounds. And it's acting there at joint B. And we need some dimensions. This is 4 feet. This is 3 feet. And we're told, we're given what the cross-sectional area of each of these are. I'm just going to write them over here off to the side. Cross-sectional area of member AC here is, if I can read my writing, looks like 0.6 inches squared. Cross-sectional area of this top member, BC, is 0.8 inches squared. And the cross-sectional area of the diagonal member AB there is 1.5 inches squared. So those are the cross-sectional area for those 3 truss members. Now, again, I'm not going back and reteaching how to analyze a truss, but we'll hopefully kind of refresh your memory a little bit. But this may require you going back and dig out your statics notes and reviewing some of this stuff. But in statics, you should have learned 2 methods to analyze a truss. One was called the method of joints. Other was called method of sections, which is kind of what we used a couple of times already. But in this case, if we want to know what the stress is in every member of this truss, we need to know what the force is in every member of the truss. And so the best way to do that is method of joints. So that's what we're going to do here, is we're going to use method of joints, again, to find the force. In each member. Again, what makes this truss special is that every member is a 2-force member. So you see all these members are pinned together. We don't have any forces applied in between the pins. And so we know the direction of the forces. In this case, since all the members are straight, all the forces are going the same direction as the members themselves. Now, before we go any further, remember this truss is being supported by a pin support here, so we will have support reactions. Horizontal, vertical reaction forces at the pin. Here at the roller at A, right, it's not actually attached, so it doesn't prevent it from moving up and down. In this case, it would only prevent it from moving horizontally. So we get a horizontal reaction force. Now, you may or may not remember, but in order to start method of joints, we have to have a joint that has no more than 2 unknowns. We're going to draw the free body diagram of this joint and apply our equilibrium equations, which, since all the forces go through one point, the moment equation doesn't do anything for us. We only have the 2 sum of the forces equation. That's why you can't have more than 2 unknowns. So if you look at a joint C first, we have 4 unknowns. We've got our 2 unknown support reactions, as well as the 2 unknown forces in members BC and AC. So that's 4 unknowns. Now, we could calculate CX and CY. We could apply equilibrium equations to the whole structure and find those. But that's extra work that we may not have to do. So let's move on, look at, come down here to joint A. There we see we have 3 unknowns. Right? We got the 2 unknown members, AC and AB, as well as our unknown support reaction. That's 3. Like before, we could find AX. We could sum the moments about C, and we could find what AX is, and we could start there. But again, that's extra work that we may or may not have to do. But if we come over here to joint B first, if you look, we only have 2 unknowns there, right? The 2 unknown members, BC and AB. So we can start there without having to calculate any of those support reactions. So if we can do less work, that's a good thing. So we're going to start here at joint B. We have our applied load of 500 pounds. And we've got the force in member BC, which the BC is horizontal. It's a 2-force member. The force is going to be horizontal. Likewise, the force in AB is going to be going the direction of AB. Now, whatever this angle is, that's the same angle. And we could calculate that angle pretty easy. Just do inverse tangent 4/3, and we could get the angle. But if you want to do it that way, that's fine. But if you notice, we actually have a special triangle here. Let me answer a question. Dylan asked, does it matter which direction the support reactions are going? No, that's strictly just an assumption. If you wanted to actually calculate those, whether your answer comes out positive or negative will tell you if you assume the correct direction or not. But you can assume whichever direction you want to. Right? So now back to our direction here for force AB. If this is 3 feet and that's 4 feet, the length of AB has got to be 5 feet, right? This is 5 feet. It's a 3, 4, 5 triangle. So I'm going to use the directions that way. I know this is 3, 4, 5. Because again, to break that force up into components, we need to know what sine and cosine of that angle is, not necessarily what the angle is. So we can get sine and cosine from the special triangle. So I'm going to go that route. All right, another observation here, sort of related to the previous question about does it matter which direction I assume these support reactions? Technically, it doesn't matter which direction I assume these two unknown forces either, force BC or force AB. But I always teach my static students to assume the unknown members are in tension. So just a note here for as the direction of AB and BC. Here, I highly recommend, encourage you to assume it's in tension. Now, if it's in tension, that means it's going to be going away from the joint. Right. Compression pushes toward the joint, tension pulls away from the joint. That's why I've assumed these two are going away from the joint. The motivation for this, assuming tension, is exactly the same as we talked about yesterday. If I assume tension, my answer is positive, means tension, and if the answer is negative, corresponds to compression. So it's a simple, easy way to differentiate between tension and compression without having to do any additional thinking. All right, we assume tension. I know positive is going to be a tensile stress, and negative is going to be a compressive stress. All right, so now we've got our free body diagram here. We got two unknowns. We can sum the forces in the x and y direction and calculate those. Now, if you notice, we have two in the x direction. So if we start there, we're going to have two unknowns. So if we go with the y direction first, we'll only have one unknown. So I like that. So let's start with summing the forces in the y direction. I'll take positive up. So what we have is force AB, the y component would be going down, so it would be minus force AB times sine of that angle, theta. But sine of that angle theta is the same as this angle, that'd be 4/5. And then we got 500 going down, and that's it. Those are only two forces in the y direction, got to add to 0. And so force AB is going to come out to be a negative, what did I get, 625 pounds. Yeah, since I assume tension, this is negative, I know that force AB is in compression. Right? So this, and again, the negative sign is sufficient there. We talked about two ways you can do plus or minus, or you can do T and C, or you can do both. We just reinforce. AB is in compression. So at this point, it's kind of personal preference up to you. We could go ahead and find the other force, and then come back and calculate the stress. Or since we got the force, we want to go ahead and calculate the stress now. We can do that as well. Let's go ahead and calculate the stress since we know the force. So I know the stress in AB. It's just going to be whatever that force is divided by the cross-sectional area. Well, we just found the force was a negative 625 pounds. And again, if you're using plus or minus for tension and compression, bring the negative along. And the area for AB, I got to find it, was 1.5 from up here. And that is a negative, what I got, 416.6666, we'll just round 0.67. And units here, force is in pounds, the area is in inches squared. So we got pounds per square inch, or PSI. Or again, if you prefer doing the T and C, it would be 416.67 PSI. And then you could say C for compression. So whichever way you want to express that, either one is okay. All right. So before we go any further, because now it's just going to be a very repetitive process, we're just going to be doing the same thing 2 more times. Questions how we got that normal stress in member AB. Okay, well then let's continue. We'll sum the forces in the x direction. So we're going to sum the forces in the x direction. They got to add up to 0. And I'll take positive to the right because that's what I see most students do. So again, we're still looking at this free body diagram up here. And we're going to add up all the x components of force, Z equal to 0. So I got force BC, I assumed was going to the left, so minus force BC. We've got force AB also going to the left, so it would be minus force AB times cosine of that angle. And cosine would be 3/5. Now, here's where we got to bring our negative along. We found force AB was negative 625. So that's force AB. And then cosine of theta is 3/5. And I believe that would be everything. And so that adds up to 0. And it's all for force BC. And it comes out positive. I got 375 pounds. Okay, it's positive. That means it's in tension. I know it's in tension by the fact that I assume tension to begin with. If you don't assume tension, if your answer comes out plus or minus, that it's not going to correspond to positive tension, negative compression. So just be aware of that. But again, to get the stress, we just take this force and divide by the cross-sectional area. So the stress in BC is whatever that force BC is, divided by the cross-sectional area. So we take our 375 pounds. The cross-sectional area of BC was 0.8. So 0.8. And I got 468.75. Again, this is PSI, pounds per square inch. Again, or I suppose if you're doing the T and C, 468.75 PSI, and then put a T for tension. Okay? So we have now found the stress in this one and that one. We got one more. Remember, we got AC that we have to find. So here's where we're going to move to a connecting joint. So we have a choice. We could go now and look at joint C, which now that we found BC, we know that one, it's not unknown, but we still have 3 unknowns there. So probably not smart to go to C. But if you come down to joint A now, we have found what AB is, so we only have 2 unknowns, AX and member AC. So that's what we're looking for. We want a joint with no more than 2 unknowns. So let's go to joint A. Here's joint A. Now we have this unknown support reaction still. We've got the unknown force in member AC. Again, I'm assuming it's in tension, drawing it going away from the joint. Now AB I know is got to act, again, same direction as AB does. Whatever that angle theta is, this is theta. But we have a choice, right? It's either going up and to the right, away from the joint, or it's going down to the left toward the joint. Right? I know it's 625 pounds. We calculated that already. But if you notice, it's in compression. Whereas tension goes away from the joint, compression goes toward the joint. This is 625 pounds. Again, this is force AB. And it is going down to the left at the same direction as AB is. And again, if you calculated that angle theta before, use the angle. If you prefer to stick with the triangle, that works as well. That's the way I'm going to do it. Again, it's a 3, 4, 5 triangle. So that's how I'm going to get my sine and cosine of that angle theta. So now we're going to apply our equilibrium equations to this free body diagram and calculate what force AC is. That's what we're after. It's in the y direction, so let's sum the forces in the y. And we've got force AC going straight up, so positive. The y component of 625 pounds would be directed downward, so be negative 625 times sine of that angle, which is 4/5. And that's going to add up to 0. AX is horizontal, doesn't have a y component. And so we can get force AC. I got 500 pounds. Again, I assumed tension, so it's positive. I know this is in tension. And now finally, last step to get the stress. In member AC, just take that force, divide by the cross-sectional area. We got 500 pounds, and my area is 0.6 up there. Yeah, 0.6 inches square. And what did I get? I got 833.333, whatever PSI. It's positive. All right, so I know it's in tension. So again, it's less work to just use plus or minus, but I'm doing both here for right now because I've seen students who like to do this that use the T and C. So if you're doing T or C, you would need to indicate its intention that way. And notice we never had to find what AX or CX or CY were. Right? We never had to calculate those. And it's always good, to be as efficient as possible. Don't do work that's not necessary for several reasons. One, in the real world, time is money, and you don't want to spend time doing unnecessary work. Two, if you're doing unnecessary calculations, you could make a mistake there that would mess up your answer. And especially on a test, when you have a limited amount of time, you don't want to use that time doing work that you don't have to do. Right? You want to spend the time you have doing what's necessary. All right, so any questions about the truss problem, how we got the force in each member and then calculated the normal stress in each member?
Yes, I have a question.
Okay.
Okay, so in this part right here, the last part where we put the force FAB and we put it actually in compression.
Yes.
So when we solved, when we did the sum of FY,
yes.
Why didn't we put it in like negative as we did before? Like, why didn't we make it negative? Is that because
so you're
we
talking about
drew?
Why didn't we put in a negative 625 here? Because I put the direction. The fact that it's negative tells me it's in compression. So I know
Right.
it's going toward the joint. Now,
Okay.
if you had drawn the free body diagram like this, I took that into account when I drew the direction. But say if we had just left it as force AB going that direction, right? If we had done this,
hmm
you wouldn't have to put in the negative 625. Does that make sense?
Okay. Okay, because we drew it in the correct direction.
Right.
So,
I drew it in the correct direction here. And so I've got a magnitude of 625 pounds going down to the left.
hmm
Right. Here, if you draw everything in tension, yes, you would have to put in here negative 625 for the force. You can
okay.
do it either way. Yeah, either way will get you the same result. Does that make sense?
Yes.
Okay.
Thank you.
You're welcome. All right. Any other questions about this one? All right. Well, then we're going to move on to the next topic. We're going to talk about shear stress, or at least kind of an introduction to shear stress. Well, you'll see later when we get to beams, there's going to be a little more complicated study of shear stress later. We're kind of limit the scope and type of problem we're looking at here, but this would be in next section 1.5 in your book. Shear stress. Kind of like the previous section, we really limited ourselves when we were talking about normal stress to basically a rod or a bar being exposed to an axial load and nothing else. So kind of similar here. This is going to be limited in scope, but it gives you a kind of a good introduction to what shear stress is. And again, this is the stress that is due to the force, right? Instead of normal or perpendicular to the cross section, it's going to be tangent or parallel to the cross section due to the force, tangent or parallel to the cross section. Right, and notation wise, we introduced this previously. For normal stress, we use the lowercase Greek letter sigma. For shear stress, we're going to use the lowercase Greek letter tau. And tau is, whereas normal stress is P over A, where P is that normal or perpendicular force. V here is what we call the shear force. It's the force that's tangent or parallel to the cross section, and A is still the cross sectional area. That doesn't change. Now, I copied. I wanted you to look at it's a picture. This is in your textbook. It's like page 32 in your textbook. It's kind of a good illustrative sort of picture and example of how we can get shear stresses on these surface areas or cross-sectional area. So if you look at this, the situation up here, you basically got this, I don't know, rectangular block-looking thing, and it's resting on two other things, and there's this downward force F pushing down on it. But if you notice here, there's going to be this cross-sectional area, and you'll have another one over here on this side. Right? When you push down on that, it's trying to shear that top block, basically shear it off if you applied a large enough force to that thing. And that's why you see sometimes scissors referred to as shears, or like lopping shears or pruning shears. Technically, they cut by making the object that you're cutting fail due to this shear stress. That's why they're a lot of time referred to as shears. You're trying to shear this cross section off. And so if you push down with this force F here, if you look at, again, this surface area here, right, you're going to have this shear force acting on that surface area. You would have this other force V acting on this surface area on the back side of that. And that's where you get your shear stress, right? The shear stress is going to be whatever that shear force, the force that's parallel or tangent to that cross-sectional area, divided by that cross-sectional area. So this, we have some area A. Now, taking this maybe one step further, just looking at this picture, if the forces have to add up to 0, right? If we got F pushing down, we're going to have a shear force V on that hidden surface. You're going to have this shear force V acting on that surface area that you can see. Well, both of those have to add up to be the same as F, right? So if the forces add up to 0, the shear force V here would be F over 2, would be half of what that applied load is. So if you were actually calculating the shear stress for this particular problem, when you do tau is equal to V over A, you would put F over 2 for your shear force V, or if you wanted to write it as that, that would be the shear stress acting on this particular, whatever this block is, or whatever you want to call it. Right? But that's what the shear stress is. It's that shear force, V, that's parallel or tangent to the surface, divided by that surface area, the cross section. Right? So it's kind of a real basic sort of illustrative example of what we're talking about. Now, I want to mention most of the problems that we're going to see in this section. We're just going to be looking at mostly joints, different types of joints where you got 2 or more members somehow or another joined together. And so that's what I want to kind of focus on right now when we're talking about these joints. Again, excuse me, we're going to see things somehow or another joined together by using pins or bolts or rivets or screws or nails, maybe even glue. So let's see, what I want to say here. So let's do this. So these are usually subjected to what we call either single shear or what we call double shear. And again, we're talking about pins, bolts, glue, etc. However this thing is being held together, it's going to be subjected to what we call single shear or double shear. And in order for you to accurately calculate what the shear stress is, you've got to understand the difference between these two. And because it's going to affect what the shear force is, which is going to affect the shear stress. Now, I have another good picture here I want to show you. This is not in your textbook. I got this out of a different textbook, but I really like the picture because it gives you a good illustration of what single shear versus double shear is. So, yeah, what you're seeing up here are all pictures and examples of what we call single shear. If you notice, again, the example they're showing here, they got two plates, look like bolted together, right? You got one bolt sticking through there, and you've got this force F applied, trying to pull the two plates in opposite directions. Well, what that's going to do is going to try to shear off that bolt that's holding them together. And so what you're looking at here, when you're doing tau is equal to V over A, the area A is the cross-sectional area of that bolt. And due to equilibrium, right, some of the forces got to be equal to 0. Right, shear force V has got to be equal to whatever that applied force F is. So the same thing would apply here. You're looking at these two, actually look like wooden boards maybe, but they're glued together. So rather than putting a bolt through there to attach these two things, right, somebody has covered some area, some part of those boards with glue and stuck them together. So the same thing is going to apply when you're getting, let's say, the shear stress here on this cross-sectional area, the surface area of the glue. You would take V would still be equal to F, but the area here would be the area of the glue, not the area of the pin, right? Now, I can draw, part of the reason I like this is it's kind of a 3D, you can see maybe better than certainly than what I can draw. But for example, I can draw real good at 2D picture of this. So let's go with like the bolt example here. Now, if you looked at this from the side, you've got these two plates, right, and you got this bolt that runs through here. And we're going to pull on this one with some force F, and we're going to pull on this one with some force F. Again, this is what we call single shear. If you got two things like this bolted or pinned together in this manner, it's what we call single shear. And again, if you look at let's draw the free body diagram of this top one here. And so if we're looking at that, our shear force V is that force that's acting on that cross-sectional area of the bolt or the pin. And again, with equilibrium, some of the forces got to be equal to 0. These got to be equal to F. So this would have to be equal to F. So it's just kind of a 2D version of what we looked at up there in 3D. But this is what we call single shear. Now you could have multiple say fasteners in single shear. So don't confuse what we're going to talk about in just a second between single shear and double shear. Go back to kind of the 3D example there. If you had this again, not pictures, this is why I didn't try to draw there. But instead of like up here where we just had the one bolt, what if you say put 3 bolts in there? Right, this is still single shear, But the shear force on each bolt would be, let's see, I can draw this. Let's go this way. So you got this force F here. You're going to have shear force V on that bolt, shear force V on that bolt, and a shear force V on that bolt. So here, again, if the force has got to add up to 0, this has got to be F over 3. And so if you were getting the shear stress on each bolt, it would be F over 3, or 1/3 of F, divided by the area of, again, one bolt. Right? But that's still considered single shear, as opposed to a triple shear. Right? If you put 2 bolts in there, that doesn't make it double shear. We're going to talk about what double shear is in just a second. Right? But does that make sense for us, what we call single shear? How to get the shear force V that's acting on each of those fastenings. All right. So last thing we'll talk about today is what we call double shear. So let me get a sheet of paper here. So double shear is come on, folks, sorry. Yeah, have a problem. There we go. Again, this is a nice 3D picture of what we would consider double shear, as opposed to what we talked about up there up top with those pictures of single shear. So here again, I can draw a good picture in 2D. I'll come back and look at the 3D picture in a second. But again, this is what we consider called double shear. Instead of just having, say, the 2 plates like that, now we actually have 3 things that are joined together. And if we apply some force F here on one plate, again, the forces have to add up to 0. So if we've got F going to the left, we got to have F going to the right. So each one of these would be F over 2. And so you can think about this one of 2 ways, right? If you look at, see, this member, where you have F here, if you think about it this way, you literally have to cut through that bolt twice, right? 2 places. You've got to slice through it there, you got to slice through it there. So V here has got to be half of that force F. When you're doing tau V over A, again, it would be F over 2 divided by A, or F over 2A. And again, that A, that would be the cross-sectional area of that pin. Here, F would be that force applied. Now, the alternative way to think about it, right? If you look at, we'll go blue. So let's look at this top member here, right? If we come down here and look at this one, we've got this force F over 2 acting to the right. And you've got this shear force V, right? That's just slicing through the bolt one place. So again, forces add to 0. V would be same as this force F over 2. But you wind up with V being F over 2, whichever way you think about it. So when you do the shear stress, you would take that force F and you're dividing by 2 times the area, or you're dividing the force in half and dividing by 1 area, whichever way you want to think about it. But this is, again, what we call, referred to as double shear. And again, coming down here, looking at our 3D pictures, might help you visualize this a little bit better. But again, when you do shear here, it's going to be F over 2 divided by the area. So you've got to be able to, when you see a problem and you're going to see, 2 members like pinned together, or you got a pin support that's holding the whole structure up, you're going to have to be able to look at that picture and recognize and differentiate between these 2 different scenarios, single shear and double shear. That's something you're expected to be able to recognize and know how to handle, right? Now, you don't really have enough time to go through and work an example. But I did want, while I'm thinking about it, one last thing, and then we'll wrap this up. When we did normal stress, I told you it was important to differentiate between tension and compression. That is not the case with shear stress. So, let me say maybe typically we don't assign, say, plus or minus for shear stress. There is no tension or compression, right? That only makes sense if you've got something with an axial load applied on it. It could be in what we call tension or compression. Shear stress, it doesn't matter. If you've got a, let's look at see, this is the cross-sectional area of this bolt. It doesn't matter if the shear force is going that way or if the shear force is going this way. It doesn't matter. The whole motivation for the plus or minus with tension and compression was due to buckling, or the material may have different properties in tension or compression. That bolt could care less. It doesn't have any effect at all as far as whatever the material that bolt's made out of. It's going to fail at the same shear stress no matter which direction it's going. So typically we don't assign plus or minus, and certainly don't refer to tension or compression, because it really doesn't matter as far as the shear stress goes, which direction it's going. All right. So I think with that, there's a good place to stop, because we don't have time to go through work an example. But that's what we'll do tomorrow. Tomorrow's Friday, finally. Yay. And we'll work a couple examples, we'll calculate shear stress. And then we'll see after that how much time we have. But that's what's coming up tomorrow. So before, again, I turn off record here, here's your chance. Any question about what we talked about today? I reckon specifically maybe the shear stress. All right. So everybody good, at least at this point, hopefully. Continue working on those suggested problems, and we'll continue tomorrow. So I'm going to turn the record off. And if, again, if you have questions about something, if you want to stick around and ask, we can certainly take a little bit of time, and I'll do that. But I'm going to go ahead and turn the record off, And then in a few minutes, we'll address if you've got any questions you want to ask. So let's stop.